Hello, this is Mr. Craig, and this is examples part 2 of day 134, solubility equilibria. I probably will make at least 2 videos. I may have to do 3 depending on the time constraints here. I'm trying to keep this at less than 10 minutes so I can post these on YouTube. Alright, let's look at example number 1. It says magnesium hydroxide dissociates in water according to the equation shown below. And it's given here. Whoops, better get the review here. Sorry about that, guys. Alright, so it says write the equilibrium expression. Again, the expression is products over reactants. So our KSP, that's a little light, let's make that darker. KSP is equal to the products over reactants, so we'll have our magnesium, and we have hydroxide. And since we have the coefficient 2 there, we'll have a square. Since there's coefficient 1, we'll have nothing there. And again, that's all equal to 8.9 times 10 to the negative 12. So magnesium hydroxide is very insoluble, has a very, very low KSP value. All right, calculate the concentration. So again, let's form an ice chart, just as we did in the earlier example. And this example is very, very similar to the first set of videos for today. Okay. So again, building an ice chart is simply for organizational purposes. It'll keep you out of a lot of trouble at times, but you should never be graded on an ice chart. So again, ICE, initial change and at equilibrium. We don't start off with anything. We increase by the coefficient x, depending on, so 1 here and 2 there. We'll finish there, 2x. So again, our KSP is equal to x to the 1 power, and then 2x squared. So again, that equals 2x squared is 4x squared. So now we have 4x cubed, which is equal to a really small number, 8.9 times 10 to the negative 12. Okay, so we can solve for x again. Cubed, let's divide that out by 4. And I don't have that one memorized, sorry about that. So 8.9 divided by 4 is 2.225, and I don't want to round too much here. Come on, pen, don't let me down. And then I want to take to find x. You take the cube root of that again. 2.25 times 10 to the negative 12. So cube that. Alright, so I get 1.3, let's say 31. And again, that's times 10 to the negative 4. Okay, so that's our x value. And what are we looking for here? We are looking for the concentration of the magnesium ions. So magnesium equals x. So this does equal our magnesium concentration. Okay, not too bad. That was pretty straightforward. Alright, part C. And we're doing great on time here. Calculate the maximum mass in grams of magnesium hydroxide dissolved in 500 milliliters of water. Again, even though we calculated for the concentration of magnesium, for every 1 magnesium ion, it is coming from 1 magnesium hydroxide molecule. So we can say that the concentration for the magnesium hydroxide is 1.31 times 10 to the negative 4. When it is saturated, or the maximum mass that we can dissolve in there. That's what that's talking about, to form a saturated solution. So, start off, if you know your volume and your molarity, always start with the volume, so 500 milliliters. Again, convert that into liters. Of course, multiply it times your molarity, which again is 1.31 times 10 to the negative 4 moles per liter. And then 1 mole of magnesium hydroxide. I know it's 50 something, but I'm not 100% sure. 24.3 plus 32 plus That's 2 times 1.008. So around 58.316. And you may notice, if you're not used to my class, I don't round anything until the very end. And I think that's a good habit to get into. So let's take that value, 1.31. I did kind of round on that one, sorry. So the maximum mass here that can be dissolved in this solution is 3.82 times 10 to the negative 3, and that is grams. So not a whole lot. I'm not sure if I could accurately measure that out, to be honest. I mean, I could get to the thousandth or to a milligram here, but I'm not sure if I can get that 8.2. But again, do realize that this is not a very good substance or a very good thing to be making a solution for, since it doesn't dissociate very well. All right, part D, it says a 0.2 mole sample of solid magnesium nitrate is added to 1 liter of our saturated solution that we just created. Assuming no volume change, does the hydroxide ions increase, decrease, or remain the same? So again, here's what we have. We have our saturated solution of magnesium hydroxide. So we have magnesium ions in solution, and we have our hydroxide ions in solution. And now we're going to add a solid here, our magnesium nitrate. Going to drop that in there. So we're adding magnesium nitrate. According to solubility rules, what's going to happen to this magnesium nitrate as soon as it hits the water? Perfect. It's going to dissociate 100% because all nitrates are soluble. So now we have in our solution nitrate ions, magnesium ions, and hydroxide ions. And again, since we are adding more magnesium ions to this solution that's already saturated, according to Le Chatelier, if we're adding more magnesium ions, oh, why my pen's not working, more magnesium ions to my solution that's already saturated, the reaction is going to shift in the direction away from the addition. Okay, so it'll shift toward the formation of these crystals. Whoa, easy there. So what I should recognize is a precipitate starting to form below, or some crystals. Let's say crystals. I don't want to talk about a precipitate. So we're actually starting to form some crystals at the bottom of the container because I'm adding more magnesium to a system that's at equilibrium. So based on that information, since magnesium hydroxide is composed of magnesium and hydroxide, my concentration for the hydroxide should go what? Should decrease. So my hydroxide concentration will decrease in this case. I think I have enough time to answer this last one. From part D, after adding a 0.2 mole sample of the solid magnesium nitrate, which was added to the 1 liter saturated solution of magnesium hydroxide, assuming no volume change, does the nitrate ion increase, decrease, or remain the same? In other words, what this question is asking is, okay, true, we added some more magnesium to our saturated solution, but what is the nitrate doing? Well, hopefully, again, you recall what your solubility rules state, and that all nitrates are soluble. So once we've introduced the nitrate ions in there, even though, yeah, it's getting a little crowded in there, the nitrate ions are not going to react with anybody. So therefore, once it's dissociated, and once we've established whatever that concentration is, the nitrate ions are going to remain the same. In other words, it will not react with anything that's in that solution, the water, the magnesium, or the hydroxide. So the nitrate ions, they're spectators. Spectators, what do? Well, if you go to a sporting event, yeah, they might scream and holler and yell, but they don't influence the game. Yeah, they think they do, but they don't. So again, they're going to remain the same. All right, so it looks like I got through this. Definitely going to have a part 2 here. So tune into part 2.